thank you, Michel, for inviting me. It's a privilege and an honor to be here and to talk to you today. I should also start out by acknowledging Michel and many of my collaborators, Steve Gervin, Leonard Glasman, Luigi Frunzio, but most especially Michel, who moved to Yale, and for the last 10 years we've had a wonderful time, and really I benefit extremely from his mentorship, his guidance, inspiration, all those sorts of things. So it's his fault that I'm in this thing in the first place. So, I think I changed the title a little bit from what was originally announced or whatever. I now have to have on the, can't fit everyone on the title slide. So there have been many people on the experiments, both past and present, and theory collaborators that I want to thank as well. It's a little bit of a family reunion here today with Andreas and Leo in the audience. What I'd like to talk to you today about is something we call circuit QED. So this is using superconducting qubits to realize quantum physics, which we can engineer. In particular, we like to use the language of quantum optics and atomic physics, which we can really use to great benefit to understand these systems. This idea of circuit QED, which is essentially a way to implement the coupling of single photons to atoms or nonlinear systems using superconducting circuits. And in particular, the nonlinear device we use is this transmon, the kind of, as Michel was saying in the introduction, the simplest way of using the nonlinearity of Josephson junctions. So something, I think they say that about good cooking. You should take very pure ingredients and do the minimum of preparation to them. So then I will tell you a couple of things. So first about some recent results where we have a new sort of physical implementation of this idea of coupled modes or microwave photons coupled to superconducting qubits in 3D, which has led to real breakthroughs in the coherence to the point where I think that's always been the biggest problem perhaps in these systems. We have some Hamiltonian description, some way of looking at quantum physics in these things, and the question has always been sort of, with these man-made artificial systems, can you ever get to the ground state? Can you observe real quantum effects? Will they be coherent enough to let you see the kinds of things you want to see, and maybe even someday build devices based on them which are non-trivial and intrinsically quantum mechanical? And so this coherence has always been the tall pole, the hardest thing that we thought we would have to conquer. And I think now, in some sense, we're probably getting to the point where we won't be able to use that as the excuse anymore. It's not to say that it won't be a problem. It's not to say that you wouldn't want to have better purity of your quantum systems. There's always room for a fresher ingredient or a more delicious LC oscillator. But I think you won't be able to blame things on this now anymore for quite some time. And then in the second part of the talk, I want to show you some brand new results. So just talked about them yesterday for the first time over in Saclay, which is using the sort of improved coherence to be able to observe some new effects, something known as the dispersive phase collapse and revival. It's a much more subtle, higher order effect that comes about in cavity QED. It's been discussed and mused about for 20, 30 years in quantum optics theory, but as far as I'm aware, never observed before. And it's the improvement in coherence that lets us see these new kinds of effects. So that's kind of one of the things we like to see if we can continue to do, is improve our systems, do something new, and then build more complicated stuff. So one of the drivers, of course, or ways that we can pay for all of this is the ideas that have come about in the last few years of using quantum systems that you can control, engineer, and eventually scale into some complicated devices to do quantum information processing. So we talk about our devices as qubits, and the basic qubits that we work with are all utilizing the nonlinearity of a Josephson junction. So very simply, a Josephson junction is two superconducting electrodes. There's some thin barrier which can allow Cooper pairs to tunnel from one of these superconducting condensates to the other. And if we think about this in terms of an electrical circuit, which is what we're going to do during today's lecture, we see that we have, well, a metal insulator sandwich. So that is immediately a capacitor of some sort. And then it turns out that this tunneling of Cooper pairs should give you, ideally, a completely dissipationless electrical element, which is an inductor. And very importantly, this inductor is nonlinear because it's going to depend via the Josephson effect on the sign of the phase difference between the two condensates. And so with this nonlinearity, we can have very schematically some sort of system where we will have discrete energy levels of this oscillator. So this LC oscillator can be quantized. And for sort of typical parameters, you can have frequencies in the few gigahertz range, which means we're a little bit better off perhaps than mechanical systems. If we can make a frequency like this, cool in a dilution refrigerator, we should be able to get right the way to the ground state just kind of passively, just by waiting for Boltzmann to set in with some thermal equilibrium. It's not, of course, always that easy, and I'll show you the best we're able to do is sort of better than part per thousand preparation in the ground state at present. And so if it's a qubit, we want to have a two-level system and not just an oscillator. And so what our levels will be is sort of the ground state, or no electrical oscillation, only the zero-point fluctuations of this oscillator. And our first excited state here will be, one quantum of microwave energy inside this LC oscillator. So in other words, the qubit is a photon. It's an odd kind of a photon. It's a very long wavelength or low energy, and it's kind of trapped. It's a bound state in an LC oscillator, but nonetheless, the quantum of electromagnetic energy is the photon, and that's the qubit. And then because of the Josephson effect, the energy level separation from this first state to the second excited state will be different. Different enough that we can, let's say, drive with some resonant tone and excite periodic or Rabi-flopping oscillations between the two states, which is the same as doing single qubit operations or allowing you to prepare coherent superpositions and the like. And for kind of these systems, what you'll see, part of the story of today's talk is that this simple picture to a large extent actually works. So these things are nonlinear at you can have nonlinearities here which are quite strong. 10% or even 100% or more can be obtained. And the dissipation can be really quite low. It's much, much better than you can do with nonlinear crystals in optics or something like that. In fact, what we can say is that the sort of ratio of loss, so we could have some resistance here, to the desired nonlinear impedance is something on the part per million or smaller level. And that's, I think, extremely encouraging for the whole future of the field. Okay, so now our frequencies, of course, the properties of these things, we like one aspect of them, which is they're under our control. We fabricate them, and they're engineerable. On the other hand, that's always a drawback because it means that no two atoms I make are ever exactly the same. It's not like working with rubidium is rubidium is rubidium. And so each of these is an individual, and the calibration issue is one that's rather significant. But at present, we can make things to specifications of sort of a % level or so, which is not so bad. In addition, some parameters of this device can fluctuate, and we can have, as I mentioned, dissipation. And those will cause dephasing of superpositions or a loss of energy where you can fall from the excited state to the ground state, which means we'll have a finite coherence time. And that's, as I said, one of these main issues, but something where there's been steady and quite remarkable progress. So again, my apologies we have some experts in the field and some who've heard these talks many times. So here's a little plot of progress in superconducting circuits. Maybe I'm missing a year or two here, and now people are up to maybe 5 or 6 qubits or 5 or 6 interacting quantum degrees of freedom, which can be engineered and controlled. And that's great, but if it's about computing, what the taskmasters or the public would like to see is something like this, where you have, the well-known Moore's law and the complexity of classical information processing devices increasing exponentially, where you double every couple of years. Now, this is not a log scale. This is only a linear scale. But if you look at other properties of these systems, such as sort of the maximum lifetime of one of these qubits, so this is the duration over which we can preserve a coherent superposition or a bit of quantum information in one of these superconducting devices. So it starts here in the late 90s with a work by Michel, Daniel Estève, and co-workers, and Saklé, and Yasu Nakamura in Japan. And the original experiments had the ability to manipulate these coherent states and preserve superposition for something like 10 nanoseconds. And this is kind of an important number because given the amount of nonlinearity we have in these systems, 10 nanoseconds is a good rule of thumb for how long it takes to do some manipulation. So to make a coherent transition from the ground state to the excited state, or swap some information between two modes or something like that. So this is kind of your entry level where you can do one thing coherently. And what you see here is that over the years there's been various experiments and various generations of devices, and this coherence time has increased quite dramatically. I've taken to calling this Schoelkopf's law. So here you get something that's even better than Moore's law, something like 10x every 3 years in the coherence of these devices. And what I'll show you in a couple of slides is 2 more generations of this continuing. So the curve I'm showing you here is kind of where we were in 2008, 2009, where you reached kind of 100 for some figure of merit, which is kind of the nonlinearity to Q factor that Michel was mentioning, right? So 100 times the time it takes you to do a basic operation means you can do some simple things. For example, Leo, when he was in our lab a few years ago, was able to use devices with kind of this microsecond coherence time and a quality factor of a little over 100 to demonstrate the first 2-qubit algorithm in a solid-state device. Okay. But as you may know, in the field of quantum information, you have to get to some higher number. There are various specifications that are quoted, but the most common number is something like 10 to the 4. If you can do 10,000 things, then you can actually build a complicated enough circuit that you can detect and correct errors and build up to some arbitrary complexity, say the theorists. So how does this advance come about? Well, in part, it comes from building things. You see a little bit of an engineering flavor in this talk. Testing them, understanding what the main mechanisms of decoherence are, and then because we have this engineering flexibility, we can either improve the basic elements or we can cheat, and we can just build something which is not sensitive anymore to that source of decoherence. And so, for instance, in these kind of charge qubits, so here you see kind of in purple in these electron microscope images, we have 2 electrodes of aluminum. The little white dots here are these Josephson junctions where you allow tunneling between the 2 electrodes. And so we have kind of oscillations of the voltage back and forth here, or this little L from the Josephson junctions and C from this interdigitated finger structure here makes that trapped electromagnetic mode, which is the qubit. And so starting in the original kind of version of these, it's exactly this same Hamiltonian, which is very nice and very simple and described by basically 2 operators, n, the number of pairs which have been transferred across the junction, and phi, or delta, the difference in the order parameter between the 2 superconductors. And this Josephson term here, this cos phi, is the nonlinearity. So these things have spectra which are nonlinear. Here I'm showing some of these energy levels, and which can be adjusted by various external methods. So even if we can't build them perfectly to spec, we can maybe tune them. But a problem you see here is that, well, it's dependent on this parameter, which is basically the gate voltage or the electric field you apply to the device. And so if the electric field fluctuates, you can have variation in the transition frequency. We will lose track of the phase accumulated by our quantum system, and we get some decoherence. One nice trick that was invented by Michel and his colleagues in Seclé is to work at some optimal point here. If you can find this kind of extremal point in the energy level separation, then you see to first order if the gate voltage or the charge or the background electric fields that this thing is subjected to fluctuate, then you will at least suppress to some large extent the fluctuations of the frequency, and things can work better. And in this sort of newer generation, so people did this, they understood that this was a good idea. It was found that basically you were then limited by the second order effects, the fact that you couldn't always tune precisely and stay at that magic clock transition or sweet spot. So we said, well, okay, let's just change parameters, make the electrodes bigger, change the ratio of these energy scales in the Hamiltonian, and then an interesting thing happens to the energy level spectrum. It becomes less nonlinear, which is bad, that's a penalty, but still nonlinear enough, several hundred megahertz, that we can satisfy this 10 nanosecond operation time. And the bands here, the energy bands, get very, very flat. In fact, they get exponentially flat, and so you can suppress this decoherence due to stray electric fields or background charges to the point where it just doesn't matter anymore. It can be completely killed. And so with this was one of those last jumps that I was showing on that Moore's law plot of coherence. One could obtain pretty reliably qubits of this transmon type that had microsecond T1s and T2s. And so again, that's allowing you quality factors of 100 or so, and the ability to sort of have an error per gate for just simple operations that's 1%. And that means that if you want to do an algorithm that takes 10 steps, you'll still have some 80 or 90% fidelity. Okay, so how are we going to use these things, and how are we going to couple them together? So together with Michel and Steve Gervin, we sort of developed an approach for doing that with these superconducting circuits that was based on the idea known as cavity quantum electrodynamics in quantum optics. So here's a little sketch. We have some resonant cavity. It could be an optical Fabry-Perot oscillator. It could be any kind of oscillating mode. And then we have inside some atom or two-level system that can interact with it. So the Hamiltonian is quite simple. You have a dagger A for your bosonic or photon mode. We have our two-level system or our nonlinear oscillator, which if we're going to just consider two levels, we can write it as a sort of pseudo-spin, 0 being the ground state, and or spin down and spin up being the excited state. And then you have an interaction here, which could be, let's say, an electric dipole interaction of this form. And the idea is to be able to use the photons here as an intermediary to carry quantum information. So we want to be able to go back and forth with our information or our excitations from the atom or qubit into the photon mode and back again. And that means that this interaction strength, which is parameterized by G, the so-called vacuum-Rabi strength, vacuum-Rabi frequency, needs to be bigger than the rates of, let's say, photon loss or non-radiative decay of your qubit or the like. And this is the so-called strong coupling regime, if you can reach it. So here's a kind of cartoon of how we do this circuit QED in our circuits. So you take your little qubits, you place them somewhere where there's a non-zero electric field in this cavity, and here's a kind of microwave engineer's version of a Fabry-Perot cavity. So think of it as a coaxial cable. We have ground planes on the outside and a center pin here. And if you have a bad connector or two, you will get reflections and you get standing waves. So here are the little capacitive gaps, which again you can tailor in your lithography, determine what the input and output coupling rates of photons are. And so we can drive the system with light, microwave light going in. We can excite the system. We can detect everything and do all of that. Now, in order to achieve the strong coupling limit, what you need is to look at this vacuum-Rabi frequency, which is basically the electric field, that one quantum of excitation in the cavity will give you, multiplied by the electric dipole moment of your qubit or your atom or your spin or whatever. And that means that you want very small cavities to make this electric field energy large. And in these transmission lines, that's really easily satisfied. So this transmission line, because it's, basically this coax can be as small as you want. The length needs to be a wavelength, but the volume effectively here can be very, very small, which increases the field strength because it's basically given by E squared over the volume has to be equal to h bar omega over 2, the 0-point fluctuations. And in addition, we can cheat by having our qubits here be very large dipoles. So the kind of typical scale here is we're transferring a pair over some microns of distance, which means that they naturally have a dipole moment which is 5 orders of magnitude bigger than God-given atoms. And in the slides following, you'll see we can make them even bigger. Essentially, if you can make the size of your emitter match the transverse direction of the cavity, very simply, you can think of it as it's very hard for light to get through this structure without interacting with the atom. And that's pretty much a good guide. What happens is you can make this interaction strength here, which in sort of normal atom systems, when done really well, is about a part in 10 to the 6 of the overall photon energy. In these circuit QED kinds of things, you can make it be several percent. And that means basically that if you want to have this interaction be large compared to detrimental effects such as decoherence, we don't need to achieve nearly as high a quality factor to have our fun and to play around and manipulate the system and so on. And so we just get to cheat. So now the sort of signature of this strong coupling is seen, for example, when you take your qubit, which would have these two states, ground and excited state, or 0 and 1, and our cavity, which has this sort of regularly spaced ladder of energy states. And if we make these resonant and couple them together, we have this interaction, which you know will give you a sort of avoided crossing, and split these levels by some amount to g. And that's something which one can observe. So Andreas sitting back there, when he was with us, was able to make devices like this. Here you have a coaxial input and output. The little squiggly thing is this transmission line cavity. Inside, one puts one of these qubits, and when the qubit is tuned into resonance with the cavity, you can see this kind of phenomena. So the cavity would ordinarily transmit at this regularly spaced set of peaks. It's a Fabry-Perot with its first resonance somewhere around here. And when the qubit is moved into resonance, you get this splitting here. So this is directly observing that kind of doublet, which is the first excited state due to the coupling of qubit and cavity. And because these peaks are separated by g, which is much bigger than the line widths, we can enter very deeply into the strong coupling limit. So you can have couplings again here between your qubit and your photon, which are on the order of hundreds of megahertz. So few tens of nanoseconds is, again, the time scale it takes to do some operation or some translation, some transportation of information. OK, so something that we do most often here is we work not in this resonant case. So here's kind of a picture of those states. When you tune yourself into resonance, we just had a cut right here showing that doublet. But if you introduce a detuning between the two systems, then these are the solution you get for your energy levels. So you see a kind of classic avoided crossing in quantum mechanics. And if you look now, you can have the energy level separation here for, let's say, adding a quantum to the oscillator is going to be modified by an amount which is second order in this coupling strength, this g squared over delta, plus some higher order terms, which we'll come to near the end of the talk. And if you like, what we get then is a kind of Hamiltonian like this. We have our oscillator A dagger A. We have our spin sigma z. And now we get this interesting interaction term where, for instance, you can think about measuring the transmission through your oscillator, which will have a certain frequency. And if we flip the qubit, because of the interaction, it will shift either down or up, depending on the state of the qubit. So this is very similar to what Michel was mentioning for the mechanical systems. Here we have this kind of quantum interaction between our one oscillator, the nonlinear oscillator, which is our qubit, and this cavity mode, which we can use now to, let's say, measure the system. So if we imagine putting photons through this cavity, we can detect either the change in amplitude or the change in phase that they acquire, which is going to be dependent essentially on whether the qubit is in its ground or excited state. So you're measuring kind of the polarizability or the dispersive effect of the qubit on the cavity. And this is, by the way, very closely related to things that are done with Rydberg atom microwave cavity QED. Now, another way to think about this is the reverse. We can also say that the qubit state, if we look at the sort of energy it requires to flip the qubit from ground to excited state, will be conditionally dependent on the number of photons. So you can use this in a nice way. You can do quantum non-demolition measurements of the qubit state using the effects, the frequency or the dispersive interaction on the cavity. You can also use a qubit to measure in a quantum non-demolition way the photon number inside the cavity. And so here's a measurement, for instance, of the shift. Here you drive the cavity with a large number of photons. You have a coherent state with some spread and photon number, which introduces a jitter in the frequency of the qubit. Now, in the kind of current implementations of this system, this interaction strength, I'll call it chi, this g squared over delta, the dispersive shift, now can be much, much bigger than gamma or kappa itself. So this is kind of a new version of a strong interaction regime. The presence or absence of one quantum in either of the two systems shifts the other one by a large amount, which is easy to measure. In fact, this shift can now be typically sort of thousands of line widths. And so this is a whole route to using the dispersive interaction for quantum manipulations, quantum measurements, or coupling quantum information. Okay, so what I wanted to do next was sort of tell you these recent results where we've been able to improve by 1 to 2 to 3 now orders of magnitude the coherences of either our cavities or our qubits. And that's by introducing this kind of three-dimensional implementation of cavity QED, circuit QED. So, so far the story was all nice and pretty. I showed you the PowerPoint version of a Josephson junction. This is an actual version of a Josephson junction. It's an electron micrograph of one piece of aluminum overlapped by the other. Underneath there is a few nanometer thick, I guess very rough, layer of aluminum oxide, which is the tunnel barrier between these things. And I have claimed to you up till now that this is all represented by a simple Hamiltonian, which is nonlinear, containing two terms and some macroscopic variables, which are represented by operators, which is the number of pairs or the voltage difference between this electrode and that electrode. And you should be skeptical, and you can see that there are all kinds of horrible things that are happening here. Superconductivity is a collective phenomena, right? And so there are many, many particles inside, and it's not at all clear that that simple description has to work. And you also see that there are plenty of technical problems here for people to worry about. You see these little bits of aluminum globules, probably partially oxidized, that are littered on the surface here after your lithography. And those obviously look like they're not good quality materials and could easily give electrical loss if I have an oscillating voltage across here. And indeed, there's good evidence that surfaces are bad in these kinds of things. So here's a sort of cross-sectional image of one of those transmission line resonators, your ground plane and your center pin. And just kind of in cartoon form, if we imagine that there are non-ideal layers that are thin, however, you can expect that if we change the geometry here, we might make ourselves more or less sensitive to the surfaces. The more tightly we can find the fields, unfortunately, the more we're going to sense dirty layers on the surface. And So if we can make the structures larger, we expect that we could do better if we were limited by, let's say, a loss tangent of the dielectric loss due to those thin layers. And this has been shown by sort of changing the geometries here. You can get factors of 2 or 3 improvement. But what we've done is we've kind of tried to take that idea to kind of an ultimate limit. So if you abandon the planar structures and go to sort of a more vertical kind of a thing, so imagine this as really a coax now, right, where you have some millimeter scale, still much less than a wavelength, but much, much bigger, not microns, but millimeters. Scale kind of a coax, again, we'll still have these dirty layers, but if you think about it, they occupy a much smaller fraction of the volume. And essentially, the influence of these dirty layers here, or this dielectric participation ratio, should just scale as kind of the surface area to volume of any of these structures. Now, it's also true that if we have non-ideal conductors, so we're going to make everything out of superconductors, but they may not be perfect, they may not be completely ideal, then we have currents that need to flow on these metals, which means that we store some magnetic energy in the surfaces as well. And that magnetic energy fraction is also reduced relative to the total as you make the scale of the structure larger and larger. And the ultimate is sort of going to a 3-dimensional cavity like this, just a box, a traditional waveguide resonator, where you'll have kind of more like millimeter to centimeter scales, and where these participation ratios can be much, much smaller. And so basically, whatever materials properties someone can realize, if you cheat and you make a bigger structure like this, you can always win 2 or even 4 orders of magnitude in terms of the lifetime of the structures, the coherence. And this is also well known. It's known that you can make 3-dimensional cavities here, which have quality factors of 10 to the 11, 10 to the 12, maybe even on some good days. So we decided to sort of test this idea that surfaces matter by going into a 3-dimensional geometry. So here's a very simple implementation of that. Just take a piece of aluminum, machine out a rectangular hole. Now our inputs and outputs for the microwaves are going to be here, and there's sort of a little pin which evanescently couples waves into the cavity and back out. So those are our little capacitive gaps. And indeed, this increases the mode volume, and right away we observed quality factors of several million, which correspond to lifetimes of storing a photon in this structure of hundreds of microseconds. By following suggestions of people who know about this stuff, for instance, using more pure materials, chemically polishing the surfaces, being a little bit more sophisticated, we've now been able to get resonators like this, which have a line width of a few tens of hertz. So this is an internal quality factor here of nearly 1 billion, or a cavity that has a ring down time at 1 photon, so the jittery blue line is a very low power measurement of this cavity, which are on the order of 10 milliseconds. Remember, our qubits and cavities previously had characteristic times of more like a microsecond. And so I think this approach is really going to pay off. In fact, the question should be here, why is it so bad? There's no reason in principle why one shouldn't be able to store a photon for a second in this way, and other people do it. So the only problem here is I said that it's, as we've heard, it's kind of Q to nonlinearity that matters, or Q to coupling strength, useful time it takes to do interactions. And so in this structure, of course, the way I've improved the Q is by increasing the volume, which dilutes the electric field strength you get for 1 quantum. And if I would put real atoms in this cavity, I would have something like a couple of orders of magnitude smaller coupling here for this cavity than for my transmission line. And so I'm not really gaining too much, especially if I'm using the dispersive interaction g squared over delta. It would all be a wash. However, we're not using real atoms. We're going to cheat again. And what we're going to do is we're going to put in this cavity, again, 2 superconducting electrodes connected by a tiny Josephson junction, just as ugly and as many warts on it. You just don't see it at this millimeter scale as before. That's maybe part of the point. And what we've done here is we've increased the size of this thing dramatically. We've just made an antenna here, which is now millimeters in size, so that the qubit electrically nearly fills the transverse extent of the cavity. Well, that's unfair. What does it mean? It means now that our dipole moment is something like 10 to the 7 times that of a natural atom. It's something like 10 to the 7 Bohr radii or 10 to the 7 Debye's. And we'll get exactly the same coupling strength, G, between a single quantum in this microwave oscillator and a single quantum of electrical oscillation in our qubit. So we can have our cake and eat it too. In fact, the nonlinearity, the properties here of the qubit, its parameters and its Hamiltonian are exactly the same. The Hamiltonian remains the same. It's just a different way of building the system. And you've also diluted the electric fields when you excite the qubit. That is to say, you've made it much less sensitive to surfaces and things as well. And also, this is an easier structure to engineer, which might be the real reason. Maybe it's just been much better at suppressing here the spontaneous emission of this device into different modes. The free space lifetime of this qubit, by the way, would be something on the order of tens of nanoseconds. But you put it in a box and try this out, and it works beautifully. So here is a lifetime now, which is something like 60 microseconds. This is putting the qubit in the excited state, measuring the relaxation back to the ground state. Here's a Ramsey experiment, 2 pi over 2 pulses, create a superposition, let it evolve, and measure whether it's still phase coherent at the end. That persists for some tens of microseconds. You can do Hahn echo and so on it as well. And so right away with this, sort of the first versions of this experiment gave 10 to 20 factor improvement in coherence. In addition, these systems look really beautiful. So, this is kind of an inverse atomic clock experiment. This is repeating a Ramsey measurement and comparing the excitation energy or the frequency of the qubit against our microwave generator, which is locked to a real atom source and perfectly stable. And you see here overnight that there's sort of one little glitch. Some dirt did something in the night. And there was a jump of about a part per million at this point in time. But over long stretches here, these things are very well behaved. They're extremely stable. And even though I can't know this frequency a priori, I can measure it, I can calibrate to it, and I can do very fine, precise control if I want to. Okay? In fact, here this frequency is stable to some number of tens of hertz on average after this long period of time. So it's really, to me, quite remarkable. I think our point of view on these things has been, let's assume that the simple picture should work, and let's try and let it do that. Let's make those simple ingredients taste delicious just by putting them on the plate in a nice way. Again, if you think about it, here's this man-made system, which I claim has some very simple, two-term Hamiltonian. It's some, nonlinear Hamiltonian as well, and it lets me predict, let's say, the basic structure of this. Here's the 0-1 versus the 1-2 transition of this thing. So this is the nonlinear spectrum, which can be predicted quite accurately once we know these parameters. But it's quite naive. I mean, it's a bit like saying, okay, a hydrogen atom is just this, right? So here you have some kinetic and some potential energy, and one of them is nonlinear. And sure enough, that allows you to predict things like the basic spectrum, the 1 over n squared spectrum of your hydrogen atom. But if you do precision spectroscopy on a real hydrogen atom, it's not this simple. That is not the Hamiltonian. That's only what we tell the first-year graduate students, right? There's a whole lot of other things. There are quantum electrodynamic effects. When you place the hydrogen atom in vacuum, it will decay in a period of a nanosecond or so. So there's couplings on the order of 0.04 parts per million for that. There are also the fact that the proton and the electron have some more complicated structure. They're spinful objects. And there are relativistic effects. So we have fine and hyperfine things, which are all also on the order of parts per million. And what I'm trying to tell you here is that for these artificial atoms, this is actually still a good description of the system at this part per million level. And we can go in, and this is what the specialists do. We look at things like the spontaneous emission, the Purcell effect in this cavity, and we try to make sure that that's something we understand and can predict at the part per million level. You can worry about what if the electrons in this superconductor are not all paired up. There are some quasi-particles or free electrons. Those can give dissipation, and what we can say is those are also on the order of parts per million, as is whatever else. I don't know what it could be, but other low-lying degrees of freedom or whatever that could couple to it. So miraculously, at least here, somehow all that dirt that you saw in the previous picture is at least separated from the system. Okay. Since those first experiments now a year and a half ago, we've made some progress on, again, understanding what now limits the decoherence in this new regime and figuring out how to improve it. So this is a measurement now of the T1 and T2 times as a function of temperature. And there are some things we understand. So the dashed line here is a simple theory that is predicting that there should be dissipation as we raise the temperature, and you begin to get quasi-particles which can be excited. So it's parameterized in terms of this number XQP, which, if you like, is kind of the probability that any given Cooper pair in the metal might be split apart just due to phonons. So it goes exponentially as this superconducting gap divided by the temperature. And of course, this predicts that in these systems we have it easy. We don't have to cool or anything like that. We should just operate at 10 millikelvin, and this lifetime should go essentially beyond a second or hundreds of seconds, because this exponential should really work in your advantage. Delta can be many kelvins. Now it doesn't, and so there's kind of a plateau I've added here to explain the fact that the lifetime is not infinite. And we don't know what that's really due to, but we can say if it were quasi-particles, here's a bound. So we know that there is less than about a half of a part per million probability that any of the Cooper pairs in the metal are actually split. And by the way, as far as I'm aware, this is the closest anyone has ever been able to prove they have gotten to the ground state of some many-body system. I think that applies even for superconducting cavities which might have a much higher Q. Those cavities, again, are sort of less sensitive. This qubit is kind of unit sensitive to dissipation. So we're relying here on the qubit and its Q of several million. It uses 100% the Josephson inductance. So any losses of that will be revealed immediately. So this fact that the quality factor of these Josephson junctions can be 1 million or more is really encouraging. And even if you don't like this particular three-dimensional style, what it tells us is that this whole endeavor of superconducting qubits really should work. Okay. Just a matter of figuring out the right way to do it. Okay, there's other stuff here, including the fact that for these devices now, the T2s were significantly shorter than T1. In fact, you would have hoped that the T2s could be as much as twice T1. And so one of the things we've worked on in the last year or so is understanding the origins of that and this sort of strange temperature dependence here, which looks familiar but is not the same. It looks like another exponential temperature dependence, but of dephasing itself. And what it turns out is that's due basically to what we call photon shot noise. It's the fact that we have this dispersive coupling. We use the photons in the cavity to measure the state of the qubit. And so any photon that passes through the cavity, or in fact any of the n modes of the cavity to which the qubit couples, does a projective measurement of the qubit state. And so your Ramsey experiments only succeed if your cavity modes were all in the ground state and stayed there during the entire duration of the experiment. It's, again, very demanding. You have to get all the way to the ground state in order to realize your ultimate coherence time. Okay? But in principle, you can just make it negligible. So here's our little rule. All of your oscillators need to be in the ground state. And again, it's supposed to be easy. All of our oscillator modes are tens of gigahertz, or they have some fraction of a Kelvin of energy. We operate nominally at 10 millikelvin. And so what's the difficulty? Well, we have to bring signals in from the outside. We have to bring information back out to the outside. And so it's not nearly so easy to make sure that you have no paths for photons to sneak in, no sources of anomalous heating, and the like. And so here's kind of a picture of that. This is the ideal Bose-Einstein occupancy of the first excited state of this cavity mode we're using for the measurement. And we can measure basically by the height of this n equals 1 photon peak the probability that you're actually in that state. Okay? And you see here that, of course, it's very favorable. If we go down to below 25 millikelvin, you know, this number of photons should just go to 1 in a million. It's very, very small. However, if we think about it and we are interested in kind of coherence times of the qubit that are tens to hundreds of microseconds now, essentially the dephasing rate here is going to be n bar, might be much less than 1, but not quite 0, times kappa, the sort of decay rate of a photon, or the average rate at which photons pass through the cavity. And so that's this blue curve, and you see that to get to 100 microseconds, I'm going to need to get at least to sort of less than 1% probability of occupying that mode. And we can see that we're not 1% occupied in the main mode, but you have to go through and include all the modes of the cavity, and there's a sort of general thing that the higher lying modes are even lower Q, faster photon passage rate, and so that's probably what was limiting us before. So here's kind of our best job of approaching the ground state so far. So here's a measurement of the cavity photon number, following this curve all the way down to about 40 millikelvin. With kind of signal and noise of 1, we think we kind of detect about 4 parts in 10 to the minus 4 of a photon occupying that cavity. The qubit, by the way, in these 3D implementations doesn't get very cold at all. So one of the things we're working on is actively cooling the qubits to get them cold. But basically, this was achieved by doing better filtering. When we look at the qubits now, we have, in the last 3 or 4 qubits, we've measured, typically the T2s are in excess of T1. So here's a T1 that's kind of 100 microseconds, T echo, which is now like 150 microseconds. So this is yet another factor of 10 improvement in the last year or so. And I should mention that this 3D thing has really taken root. There's something like 6 or 8 groups around the world who have immediately jumped on this, reproduced these results, and gotten sort of comparable coherence times. So I think the field has become now very vibrant, and when somebody has a good idea, it can be picked up, and so we'll all be sort of working from here in the future. And what I think I like even more is here's sort of T1 versus that thermal excitation curve, and now the red is our T echo, and the green is kind of a notional theory of that photon-induced unintended measurement as a source of dephasing. You see that it tracks quite nicely. So I like the fact that we can not only improve the coherence time, but understand it. And I think you see here that probably it's a matter of getting both the quasi-particles, the qubits themselves, the photons in these cavity modes we're using. The more we can drive the system toward the ground state, the more we can understand how to get rid of just the simple loss, the better the coherence can be. And I think we certainly haven't seen the bottom yet. So here's now the Schoelkopf's law plot repeated. So here's where we were about 2008, 2009 at about a microsecond, or the ability to do 100 operations. When I put these new points on, you see we've followed another 2 orders of magnitude improvement. And now we are getting really kind of close to a level of 10 to the 4 for the ratio between how fast you can do an operation, tens of nanoseconds, and how long you can preserve a quantum bit or some state that you're trying to manipulate. Now that's far from saying that one can now trivially do operations at 10 to the 4 errors. Okay? But what it does say is that at least just the fact that you're waiting around and there was dissipation and decoherence in the system while you were doing your operation shouldn't be the limit. And so a really interesting thing is kind of how do we push to systems where not only do we engineer the Hamiltonian, but we know all the terms in the Hamiltonian at the level of 10 to the 4, or how to avoid them. But I think it's really encouraging. And you see here the 3D cavities, too, are even a couple orders of magnitude higher. So another thing that we're sort of thinking about is a perspective where if you have a memory or an oscillator you can use to store a quantum for a very long time, that's something which is a resource we've never had before in these systems. That probably changes the way you want to do operations, the way you want to think about things. Okay, so maybe in the last 15 or 20 minutes here, what I'd like to do is take a little bit of a different direction and instead of telling you about the progress of the field and the engineering things we have to do to make the systems nicer and nicer, I want to give you a very recent set of results where essentially when we can improve the quality factor of these systems, we can see ever more subtle, newer kinds of simple quantum effects. And so I want to show you the work of Gerhard Kirchmeier and Brian Vlaslakis with theory support from Maziar Mirahimi and Zaki Lektas about what I believe is the first observation of what I'm calling the single atom, single photon Kerr effect. So this is an effect which is, so the Kerr effect is kind of the simplest nonlinearity which one can have. So it's exactly the same thing as we have in our qubit, by the way. It's just saying that the index of refraction depends on intensity, or the energy is something other than just a linear function of n, the number of excitations, the number of quanta in the mode. So this Kerr effect is a favorite of quantum theorists, quantum opticians, but it's typically very hard to realize, except in these Josephson junctions, one can really do it. It's quite nice. So this experiment is also kind of trying to work in the direction of scaling to more complicated things. So kind of in concept, we have our spin or our qubit, which is now going to be coupled to two optical microwave modes. And we're going to have basically a Josephson junction-based qubit, so two electrodes with a Josephson junction, that's our little symbol for a Josephson junction between, to give us a nonlinear LC oscillator. And we're going to place it kind of in a channel between the two cavities with little antennae that stick in to allow you to tune the coupling to a photon mode here or a photon mode there that might be at different frequencies, hence the different colors. That's a picture of what it actually looks like in this 3D implementation. And in a little more detail, if I zoom in here, you see a little sliver of sapphire on which there's a superconducting film. And at this point, where it sort of looks too small for you to see, there's a little Josephson junction that couples the two. So this is just another mechanical or physical implementation of that simple transmon qubit. You have two electrodes, and you can have oscillating voltages across. And then you see here a wall of one cavity and the other where it's extending in. Okay, there's the Josephson junction itself. These systems, we've also worked on sort of how to understand them and how to design them. So one of the things that we really like about these quantum circuits is that one can take the tools of electrical engineering and use them to kind of design and specify the properties of the system, and then from that write down a Hamiltonian. The thing, of course, we'd really love to do is say, you tell me the interesting Hamiltonian you want to study, and I tell you where to put the metal. That's sort of where a lot of our work comes, is in figuring out how to go from one to the other. But there's actually a very simple way of viewing these things, which is I have the place where I'm going to put my little Josephson junction, my little inductor and capacitor. And the rest of the world essentially is just some impedance, some electrical network which will give a certain relationship between currents and voltages as a function of frequency across that junction. And so in these things, we're sort of forced to understand both lumped elements, distributed elements, as well as 3D things. This is not important, but just, there's tools you can use to kind of analyze these. And you can basically simulate in different packages, put together and synthesize your network, and then work to get the Hamiltonian. And we have a kind of improved way of doing this, which, well, I'm sorry to say, Michel and others, we're kind of trying to circumvent a bit the Jaynes-Cummings Hamiltonian and the cavity QED style. But basically, if we start with kind of a linear inductor, this is, of course, the Hamiltonian of an LC oscillator, just you know, an N and a phi. Oops, that should have a hat on it. Oh, and that should be squared too. Sorry. But basically, you know, it's just a quadratic Hamiltonian, so the energy level spacings are all completely linear, and you can write down some second quantization. You can have some raising and lowering operators, A's and B's here, for the various modes. And at a minimum in this structure, you have to have the three modes. There's the localized mode of the qubit, sort of shown in green, the red and blue modes of the two cavities. So we start with kind of the whole structure and the linear part of the Josephson inductance. So this is just approximating cosine by 1 minus phi squared. And then we can add as a perturbation the actual Josephson junction itself, which has quartic and sixth order terms in this phi, the phase difference across the junction. And what that does in this kind of oscillator language here is immediately it says that all of the oscillators become a little bit nonlinear. Okay. The qubit mode, of course, has current flowing through the Josephson junction, and that gives this cosine phi, and it gives an important quartic thing that gives me this few hundred megahertz nonlinearity of my qubit mode. But if you think about it now, when these things are coupled, there's actually some amount, it's always non-zero. If I excite one quantum in this upper oscillator, there'll be some current which can flow through the Josephson junction, which gives directly a quartic term for it as well. And so in this three-mode system here, I'm going to have my qubit, which is the B daggers, which has an anharmonicity here, which is very large. And then I will also have a non-zero anharmonicity or Kerr term. So this is a part in the Hamiltonian here, right, going as n squared with this Kerr constant k. And as well, there are these dispersive couplings between all the modes, which we talked about before. This was the g squared over delta term, the sort of second order if these frequencies don't match, thing which says that if I excite the qubit, I shift the frequency of the cavity and vice versa. And in fact, all of these modes here will have a dispersive coupling which is large and which can be observed. And kind of the current state of the art here is if we do these things carefully, and if we allow ourselves one extra measurement, which is after we make the Josephson junction, we probe it at room temperature, we measure just its resistance, which, knowing the superconducting gap, you can relate to the size of the critical current, or this Josephson inductance. Then one can develop this entire Hamiltonian here and get all the parts of it right to a few percent. So it's not perfect, but you know, it's a lot of progress, actually, for us. And there's also an important rule here, which is going to be really critical in the future. So if you want to have, let's say, a coupling chi between things so that, I don't know, you can measure the excitation in one mode with another. So you want to have this chi between things. It means that you need to have nonlinearities, and that if one mode has a certain nonlinearity, the other one will inherit a nonlinearity as well. And so this is good sometimes and not good other times, because if you, let's say, want to be using one of these cavities as a memory, you would like it to really be a very simple oscillator. Now, this Kerr effect you can also kind of understand in terms of cavity QED. So again, if you take your Jaynes-Cummings Hamiltonian and in the dispersive limit you write down what the energy levels are. So this is the exact diagonalization. And then when you have a large detuning, you're in this dispersive limit where delta is greater than g, you can kind of Taylor expand this thing. And again, the second order contribution here is this chi dispersive shift. And if we keep going, there's something which is fourth order in this interaction. Remember, with sort of natural atoms, I said g here, you know, delta is some fraction of omega, so this g over omega here is something like 10 to the 6. So typically, these terms are not observable. But for us, they're going to be, because even if this is a few percent and we raise it to the fourth power, it's still going to be large enough to observe. So this Kerr effect kind of occurs in this cavity QED language as well. So, okay, running a little long, but let's see here. So let's cut to the chase. So if we drive an oscillator we have a displacement, and we just couple it to a classical field, we'll tend to make what are known as coherent states in the oscillator. So those have some coefficients if you express them in terms of the energy eigenstates like this. And this alpha, this size of the displacement here, is a complex number which tells you about the amplitude and the phase of the fields that you create inside the oscillator. It's related, of course, to the amplitude and phase of the drive that you apply. And if you would create some coherent state and let it just evolve under a typical harmonic oscillator's Hamiltonian, just A dagger A, you will get, of course, some phases that these coefficients acquire, which is just proportional to n. So it's kind of a linear set of phases, and that just means that your number alpha, this complex number here, acquires a phase which rotates, of course, at the frequency omega that you are using for your oscillator. So the typical thing is, of course, we lock an oscillator to the cavity frequency. We'll talk about all the phases relative to that reference oscillator, and we can go into a rotating frame. And so we displace, it would oscillate around, but if you go into the rotating frame, it'll just sit there. Okay? Everybody good? A little bit more precisely, what you can measure for a quantum oscillator is something known as the Q function of the oscillator. The Q function is defined as such, and basically it's sort of the projection of the density matrix of your oscillator onto the coherent state basis alpha. And so what that does, if you have a coherent state, is now instead of getting a point in this IQ space for your alpha, you have a little disk. The disk has a full width half max of 1 in sort of natural units. That's the vacuum fluctuations of the field. And we can use this, we can basically measure the Q function of any sort of state. Let's say I prepare some state like that. What I do is I have to do tomography. I want to measure basically the projection onto the ground state or the vacuum after I apply various displacements with different alphas. So the way we'll measure this is pretty standard in quantum optics. You know, displace the state over there. That would have no overlap with the ground state, so I would add over here a point which is just an empty box. If I'm here and I displace so that it has some nice large overlap with the ground state, I'll put a darker point for the higher density probability of finding us at that point in the IQ space of the oscillator. Okay. So how do we do this? Well, we use this number splitting. So here again is the spectrum of the qubit. This is the frequency for n equals 0, 1, 2, 3, 4 photons, et cetera. So we can measure directly the probability of, let's say, being in the ground state if we just have some state in our cavity and we Rabi flop the qubit at this particular frequency in a frequency selective way. The probability that I can excite the qubit at this frequency is exactly the probability of finding my cavity in the ground state n equals 0. And so on. And in this experiment, these peaks are separated by some hundreds of line widths, which is good. So let's try and do this experiment. So what we'll do first is varying amplitudes of an initial coherent state displacement, and then measuring the probability of staying in the ground state of the oscillator. This is P of 0. It goes like this. If we measure P of 1, 2, 3, up in this experiment, we can measure up to n equals 7 independently. So we can measure directly the probability of finding this gigahertz oscillator in the n equals 4 Fock state. Okay? And now basically what we can do by fitting this dashed line, which is just this probability you expect for a coherent state, we can scale this axis, and that's the only calibration needed in this experiment, and say, okay, that corresponds to an alpha of 1. This DAC level corresponds to alpha of 2 and the like. And now if I make a coherent state and then analyze it in this way, here's what I get. So this is something like 400 different alpha displacements, measuring the probability of finding myself in the ground state. I find this blob like so. If we look at it, they look like nice Gaussians, just as they should. The width, which has just been calibrated using that previous distribution, comes out to be 1, and everything is nice. So now, let's do this and analyze the states of one of these oscillators which has inherited a Kerr term, I claim, from my qubit. We'll look for the fourth order term in g squared over delta. This kind of evolution of an oscillator with a Kerr is, again, something that's been discussed a lot. Here's this paper from 1986 discussing a way to make interesting non-classical states, including cats, using a Kerr evolution. Has like 750 references. It's described in this beautiful book by the École Normale group as a nice thought experiment. Let's do it. Okay, so what was going to happen here is now, instead of just the linear phases that we acquire, we will have an additional quadratic in n phase that accumulates in time. That will mean that basically the different Fock states that I include in my coherent state will have different time evolutions under the influence of this term. Okay. And for instance, this will have a special property. If I weight sort of an inverse Kerr constant, I will get all the way back to 1. Everything comes right around again. If I wait for half of this time, then the phases that I acquire here will be like -1 to the n, which is just exactly what you get if you take alpha and put it to minus alpha. Okay. But at other times, more interesting things will happen. If we wait some time, which is, again, half of this Kerr constant, or 1/4 rather, then what you expect to get is a coherent state that evolves into this interesting non-classical state, cat state, kitten, anyway, a few photons. And in fact, you should get many, many such non-classical states for every sub-integer multiple of this time. Okay, so we'll do this. We're going to use one of these oscillators that has a Kerr constant of a few hundred kilohertz, which would have been always immeasurable before, but now is something like 20 times the decay rate of the cavity. And all right. So here's, I'm going to show you a little movie. Here's the prediction from that simple Kerr Hamiltonian. Here's the measured Q function after an initial displacement. And let's go over to here. And so here's the time after preparation of the coherent state. And again, these are the measured distributions and the predicted ones. So right after the distribution, you see it's not quite perfect in this case. It's a little bit dropped, for instance. Now remember, our Kerr constant is negative. So what happens here is that depending on n, the different Fock states kind of acquire a negative phase relative to my rotating frame, which is proportional to n. And so you see that our coherent state, which starts as this nice blob, now has a kind of rapid smearing or collapse. Okay? And the idea here is that basically, instead of in a linear oscillator, now there's no single rotating frame, if you like, that works for all amplitudes of the fields in the cavity. So if we continue, you see that things get more complicated, but interesting stuff sort of occurs. So right around here, you see we end up with kind of 3 Gaussian blobs. It's kind of a 3-component Schrodinger cat, just as would be predicted by the Kerr effect. And if we continue on, things kind of rephase. This is just a kind of revival mechanism of a new type where because the phases that are acquired are equal but just quadratic, we get this reforming. And if we continue again, you see a 3-cat, a 4-cat, and eventually a coherent state with this reversed phase. And if we keep playing the movie forward, it goes again, a 4-cat, a 3-cat, a 2-cat, and eventually it sort of reforms again on the original one. And by the way, this was done not with our largest Kerr constant, but with one that was small enough that we were able to do good analysis on it and sort of show you the movie. And there's obviously some imperfections here in the revivals. Actually, the 6th order in G term is probably not negligible. It's probably a 5 or 10% effect here. And also the qubit's not perfectly in the ground state, which gives some dephasing. Okay. And it was kind of fun as this is a new piece of quantum optics. Of course, a cavity which has a controllable and measurable Kerr effect is a neat building block for creating nonlinear quantum systems, nonlinear quantum states, and the like. So this is kind of fun. And basically, this required this 2-cavity experiment in essence so that we could use one cavity to do the measurement of the qubit and extract the photon numbers. So we can also look at things beyond the Q function. So that kind of a blob you could get from a mixed state. Of course, the mixed state, which is probabilistically two coherent states, wouldn't reform. But anyway, what we can do is we can measure the projections onto all the different Fock states. And this is done for this kind of 2-cat. You see here these kind of fringes in between, which is a real signature of the fact that you have this quantum superposition of two coherent states generated by the Kerr evolution of the cavity. And if you measure all the n's, you can reconstruct the density matrix. And from that, one can look at things like the Wigner function. So here's the calculated Wigner function for that 2-cat and our measured Wigner function. And again, these fringes are the signature of coherent superposition. And the negativity of these Wigner functions is what tells you it's really a non-classical state. So these kind of Wigner functions have been beautifully described, measured, and watched as they decohere in the Rydberg atom community, and also using a rather different route of kind of synthesizing by brute force the various Fock states. All kinds of interesting non-classical states have been synthesized using superconducting qubits in a sort of a different style by the group at Santa Barbara. But for us, this was kind of fun because it's the first time we got to play with the Wigner function. So there's Wigner functions for the 3-cat and the 4-cat. Basically, you see, by the way, up to an n-component cat where n is the biggest initial coherent state displacement you make. Otherwise, they kind of smear together. So this was alpha of 2 or n equals 4. But we think that this would scale much better to large numbers than, let's say, that n by n synthesis technique. So I think we can talk about the future of this field. Again, the fact that the coherence can be so good is really encouraging. I think the various advances, including, for instance, advances in making non-demolition measurements, having amplifiers that work right at the quantum limit, which is something that Michel's group has been pushing, as well as several others, means that we're really now in a point where we have a Lego tool set. We can make interactions between quantum objects in this electrical circuit world. We can array them in interesting ways. We can now start to measure them or do complicated enough gates that I think we're going to be sort of entering this era of what I'd like to call active quantum devices. So instead of, let's say, just trying to make fancy superpositions between a few qubits and do as many rapid manipulations as you can before the clock runs down and your oscillator decays, now we can look at issues such as quantum feedback, autonomous quantum error correction, and so on, and see if we can really do something non-trivial with a handful of interacting quantum degrees of freedom. And hopefully there will even be some applications that don't require us to build a 1,000,000-qubit Shor factorization machine. Okay, so it's probably kind of lunchtime. Let me thank the many people who've worked on this. Again, there have been people over a decade or so doing lots of things. This is the current group. Honey Peck is the postdoc who sort of pioneered the three-dimensional stuff. Matt Rager is the one working on high-Q 3D cavities. Adam Sears is the one who's done the work on photon dephasing. And Gerhard and Brian are the ones, together with our theory colleagues, who've been driving the two-cavity and this Kerr effect and cat states and so on. So I'll just put up my last slide. Thank you again, Michel, for having me. Thank you for staying and listening. Merci.